Similar as there was a simplex method which essentially created a smart path among the extremal points to find the optimal solution, there exists a clever algorithm which only needs to check some of these combinations. And that clever algorithm is called the active set method. And that's what we are going to cover now. Okay? So as any algorithm similar to the simplex, we had to start from some feasible solution. Here, moreover, we are starting from some initial active set. Now, how to get this initial active set, that's a different story. What you can always do is to take initially, so if this will be kind of the iteration number 0, what we need to find out is the initial feasible x. Which conditions does this initial point have to satisfy for it to be feasible? How can we check whether an x is feasible? I give you particular representation of this optimization problem, meaning I give you matrix P, vector Q, matrix A, vector B. I also give you an x. I ask you, is this x feasible? Does it satisfy all constraints? How can we check that? We can check the constraint. Ax less than b. If all constraints are satisfied, it's a feasible point. Okay. So we need the feasible point which satisfies this property, and we pick some initial active set. And what we can do is we can just set it to an empty set, because we know that in quadratic programming, even no constraints could be active at the optimum. So that's what we do at the initialization phase. And now come the iterations of the active set method, which are kind of similar to pivoting operations in the simplex algorithm. Okay? So at each iteration, what we are doing, let me see if I have red color. I do. And let me draw a larger version of that example. So these are the constraints. Let us suppose that the cost function is first like this. Okay? So no constraints are active at the optimum. Let's furthermore suppose that this is the initial point. I would call it x0 like for the 0 iteration. Okay? This is the point we know, and we would like to improve the point. Okay? Therefore, we would like to find a new point, this one, and we can find this new point, let's call it x1. The new point is clearly given by x1 is x0 plus some step length times delta here. Okay? So let us find this delta which says by how much should we move from the initial point such that we reach the optimum of this function. And this delta we can very easily obtain by solving that optimization problem. So now we are optimizing with respect to delta, because x here is a constant. That's the initial setting of the feasible point. Okay? So we are optimizing for delta, which solves this optimization problem. And we are assuming that these are the constraints which we are considering to be active right now. Okay, so let me write by A indexed by W just the rows of A which are indexed by the set W. So if the set W is empty, it means we have no equality constraints. Now, how can we find the delta which minimizes this objective function subject to these constraints? We solve the KKT system. So what would be the KKT system? So we need to write the Lagrangian, right? So what's the Lagrangian of this problem? It's 1/2. Let me expand that. Okay? So we have x transpose px. That's from here. We have delta transpose p delta, and we have q X transpose P delta, right? Now we have plus Q transpose X plus Q transpose delta plus lambda transpose times AWX plus AW delta minus BW. The optimization variables, oh, sorry, I made a horrible mistake. Lagrangian is not a function of X, but a function of delta, because X is constant here. So what is now the gradient of the Lagrangian with respect to delta? So this one is not a function of delta, so it's 0. Here it's 2p delta, but we have 1/2 in front, so it's just p delta. Here the derivative is we have to transpose this whole stuff. Right? And this 2 cancels out with this 1/2, so that's just P transpose times X, but we know that P is assumed to be a symmetric matrix. So P is equal to P transpose. Okay? Plus, this term doesn't depend on delta, so the derivative is 0. Here we have just Q. Now, this term doesn't depend on delta, so the derivative is 0. And here we have just AW transpose times lambda, and that's it. And we know that the optimum, this must be equal to 0. And what is the gradient with respect to lambda? That's just this term here, right? So it's just AX, AWX plus AW delta minus BW is equal to 0. So the unknowns that we have here are X and lambda. Lambda and delta. Okay? We see that both of these equations are linear in those unknown variables. So we can actually solve for delta and for lambda by solving a system of linear equations. So here we have the multiplier in front of delta is P. The multiplier in front of lambda would be AW transpose. The right-hand side is this term here. Right? So it's minus PX minus Q. Here we have AW as a multiplier of delta. Lambda does not occur in the second equation. And the right-hand side is just, well, we have to put it to the right-hand side, BW minus AWX. Now why, or what can we say about this term here? We are assuming that that X was chosen such that it is prime or feasible. And actually, since we are assuming no active constraints here, it just means that this term here is 0. Okay? So here we have 0. So essentially, we are at iteration number 1. Okay? Where was it? We are assuming that the original active set is 0. Actually, what does it mean that if the original active set would be 0 is that these terms here would just disappear. So in the very first iteration, we are just optimizing with respect to delta because we have no constraints. W being empty means we have no constraints, so we don't even have to include lambda into the calculations. But we would need at subsequent iterations. So what we have just done is we have found the lambda, which minimizes the objective function, subject to these active constraints, currently with respect to no constraints. And now two situations could happen depending on the value of delta and the value of the corresponding Lagrange multipliers, which I'm calling me here, okay, to be consistent with the equality formulation. First of all, what could happen is that we have a situation like this. Imagine that we have an objective function like this, and I try to make a relation to this one, but it will not be so easy. Okay. Okay. Let's do it this way. Imagine that we have started here, and what the delta will tell us is this point here. Okay? Clearly, there is a difference between these two situations. The first one is feasible, satisfies all constraints. The second one is infeasible. In both cases, we have found a point where we are already at the optimum. Essentially, if we would apply one more iteration, then we cannot improve the solution anymore, because we have already found the optimum of the original problem by only considering a particular subset of active constraints. So the first scenario happens when this delta as a solution to that system of equations is 0. It either means that we have already found the optimum, because delta equal to 0 means I cannot find a better solution that I already have. Okay? If we cannot find a better solution, still we can consider two versions. Either all those Lagrange multipliers that we have found as a solution to the KKT system, if all of these lambdas, which we will obtain by solving this system of equations, if they are all non-negative, what does it mean? What does it mean that we have found that we cannot improve the solution anymore? When can we not improve the solution anymore? Where x is already the optimal point. Simultaneously, we have found that all lambdas are 0. What does it mean with respect to the Karush-Kuhn-Tucker conditions? Is the solution optimal or not? If I would tell you, let's try this x and this lambda, I would just give you a hint, like try these values of x, these values of lambda. How can we certify that the solution that I told you is optimal or not? Well, we check the KKT conditions, right? So we check stationarity, we check primal feasibility, dual feasibility, and complementary slackness. Actually, if the lambdas are all non-negative, and if delta is 0, and if x is primal feasible, then we have just found the optimal solution. In other words, if it happens by chance that at certain iteration, for some active set, we find out that delta is equal to 0, and all lambdas are non-negative, then we can abort the iterations because we already have the optimal solution. So that's option number 1. However, what can also happen is that we find that delta is 0, but we have one of those Lagrange multipliers which is negative. Well, by Karush-Kuhn-Tucker theory, it says this cannot be an optimal solution, because an optimal solution must have all Lagrange multipliers being non-negative. Okay? So what do we do then is, essentially it's a situation like this. Somebody told us, let's say that the situation is like this, that this is the optimal solution. Somebody would tell us, consider as the starting point this point. Moreover, consider that among these 4 constraints, so this would be 1, 2, 3, and 4, consider that initially constraint number 1 is active. essentially what we will find out by solving this system of equations is that since we are assuming that constraint number 1 is active, we are only allowed to move from this initial point by some delta either in this direction or in this direction using some step lengths. We cannot go in any other direction because we are assuming that constraint number 1 is active. Essentially, regardless of which direction you go, you will not find an improvement of the objective function because the objective function improves in this direction. But since we are assuming that constraint number 1 is active, we cannot go into this direction. Okay? So here in this particular case, we would have delta equal to 0, means regardless which way I go, I cannot improve the solution. However, this point is not an optimal point because one of those Lagrange multipliers is negative. Okay? Then what we have to do is we have to change our set of active constraints. We have to say, maybe we were too optimistic here. We said constraint number 1 is active at the optimum, but apparently it is not active at the optimum. So we have to remove that constraint from our active set. Let me give you an example which explains the other part of the sentence, because I will just make up some numbers. Say that the set W, the set of active constraints currently is 1, 5, and 8. Which means constraints number 1, number 5, and number 8 are potentially active at the optimum. Let's say that by solving this system of equations, we obtain the lambda, which will be a vector like this. 2.5 minus 4.8. Okay? So what it means here is that, of course, we would like all lambdas to be non-negative. So this obviously is, this value is fine, but one of these values are not fine. So essentially it means the solution is probably not on constraint number 1 and number 8. And now we have multiple options. What we could do is to say, let's remove from W 1 and 8. So let's suppose that the next candidate that we are going to try out is just 5. However, this would be jumping too far. And this is, yet again, where this procedure is quite similar to the simplex algorithm. We just get iterations and heuristics, okay? And the heuristic says, remove the constraint which has the smallest negative value of the Lagrange multiplier. So the next candidate that we would be considering is, in fact, 1 and 5. Okay? And nobody says this is the best way with respect to convergence. It might be that removing this constraint is more beneficial to the speed of the algorithm. But yet again, it's an approach which works well in practice for majority of examples. Okay? So essentially this first case means we have started from some initial point and from some initial active set. We have found out that there is no improvement of that initial point. So two situations could be. Either we have found a solution, and the solution is certified to be optimal by non-negativity of the dual variables, or it can be that there is no improvement, but that improvement is because we have a wrong constraint in our active set. So we will remove one of those wrong constraints. Not all of them, just one of them. The one which corresponds to the smallest entry in the vector of dual variables. Okay? So that's essentially this situation. But what could also happen is a situation like this, and let me do it here. Let's suppose that the cost function is here. Okay? So here we have the initial point. Clearly, by minimizing delta, by solving that problem, we would find this point as our next candidate for the optimal solution. So now we are in the case where delta is not equal to 0. Okay? However, maybe I shouldn't have wiped that. Actually, we can have two situations like this. What is the difference between this point as x1 and this point as x1? This one is a good point because it is still satisfies constraints, and that one does not satisfy the constraints. So if it does not satisfy the constraints, we have to actually add a new constraint to our active set. So now we have to determine, we are in a situation where we have found a non-zero delta. We have to find out whether possibly some constraint will be violated by going into the direction of delta. Okay? So what we are saying is the following. Let's say that I have a constraint like this, Bj. Let's suppose that x is fixed, that's the input to our iteration, and we have just optimized delta. And we would like to find out whether we are in this situation or in that situation. How can we check whether by moving into the direction of delta, so if this would be x0 as the input to the iteration, this is x1 as the output of the iteration, how can we check whether this new point satisfies all constraints? Again, we just look at whether all these conditions are satisfied. If they are satisfied, we are in the good case, we just move to the new point, and we don't do anything about the active set. However, what can also happen is that we were too aggressive. We said that the delta is too large. If I would just add it to the initial point, I would end up in a point which is the true minimum of the quadratic function, but unfortunately the point violates constraints. So now we have to find out which constraint will be violated first by going into the direction of delta. And here in that box example, it doesn't make much sense, but let's suppose we have a situation like this. Okay? Let's suppose that x0 was here, and the cost function has level sets like this. Okay? So what we would find out by solving this iteration here is that we would need to move into this direction to find this point. But this point obviously is not feasible. Obviously there is a constraint which stops us on our way towards this true optimum of the unconstrained problem. We need to find out which of those constraints is stopping us. Again, there is a relation to the to the simplex method. It was about those ratios. Which constraint stops us first when we start increasing some variable towards infinity? It's the same here. Again, we are asking, which constraint stops us first while moving from x0 in the direction of delta? And how can we find it? Essentially what we are looking for is that if we prolong these constraints, then these are the intersections between the individual constraints and the line segment which connects x0 and x0 plus delta. That's the point x0 plus delta. We are asking ourselves, which of those constraints, let us number them, 1, 2, 3, and 4, 5, and 6. Which of those 6 constraints stops us from violating the feasible set? Essentially what we have to, if we are looking at a violation, we have to look at where is this one larger than Bj. Okay? Actually, we can also find out the precise distance from the corresponding constraint. What is the distance of this point from x0? Let's call this distance here beta 3, like the distance from the third constraint. Any hints?
Wouldn't it be all a little simple when we would start set of initial active constraints with all the constraints, and then just removing.
That's an interesting alternative. The problem there is that here, in order to remove some constraints, we are removing it based on lambdas, correct?
Yeah.
To get to this logic, we first need to know lambdas. If you just throw in all constraints, this problem wouldn't have any solution. Because you are saying the solution simultaneously lies on all constraints. Obviously, that's not possible. Even in the box, it is not possible. Therefore, this system of equations is infeasible, so you have no values of lambda based on which you could base this logic. Does that answer the question?
Yeah.
So that's the problem. That's why we have to start from an empty set and add new constraints on the fly and remove constraints on the fly. Okay? So if we have a delta, an improving direction, for which even the improved point satisfies all constraints, that's the easiest case. We just move to the new point without changing the active set, and we repeat the iterations. We say that this is now the starting point for the iteration. Let's improve it even further. Okay? However, what can also be is a case like this. We have found an improving direction, but it leads us outside of the feasible set. So we must stop somewhere. And actually, this is the distance of the point of this intersection point from this point x0. Okay? So this beta here, beta j, let's call it beta j for the j's constraint, or it's I there, doesn't really matter. So it's bj minus aj x0 divided by aj times delta. That's the distance of this intersection point from here. So then what we do is that we evaluate those distances for all possible constraints. But we do it only one by one. So we find out what is the distance in going in this direction from this constraint. Here, if this direction would be parallel to this constraint, that distance would be infinity. Okay? If we have a non-parallel constraints, then here this point is beta 2. This point here is beta 4. We don't need to consider beta 5 because that's again parallel to this constraint. And we don't need to go into the negative direction because we are only considering the intersection between this line segment and this constraint. So now we have all those distances, which will tell us which constraint will be violated first by moving from point x0 towards the point x0 plus delta. And what this figure tells us is that beta 3 is the smallest among beta 3, beta 2, and beta 4, the smallest value, because it is the shortest distance to this point. Therefore, the solution must be stopped by constraint number 3. So this is nothing but a fancy version of that pivoting logic that we have used in the simplex algorithm. In simplex, it was easy. Just look at the ratio between the right-hand side and the leading coefficient of some variable. In the active set method, it's a little bit more involved. What we need to consider is not just the ratio, but some kind of an extended ratio. But you see, I mean, it's really the same thing. It's a ratio of two numbers, and this is the distance of the intersection between the line segment connecting these 2 points and the corresponding constraint. But it really answers the same question as in the simplex algorithm. How to choose the constraint which must be considered for an improvement in the solution. So what we do now is that we evaluate these distances for all constraints which are not yet in our active set, and we add to the active set the constraint which has the smallest positive value of this distance. So yet again, we are only looking at positive distances. So that means that the output of this iteration is that we have a new point, x1 is equal to, that we have a new active set, which is W, which is the same W as before, but this time we also add to it the index for which beta was the smallest one. So in our case, our W originally was an empty set, so after this iteration, so this V1 would be just constraint number 3. Because clearly constraint number 3 has the smallest distance of this intersection point from the original one. So we have a new candidate active set. Nobody is saying that this is the optimal active set. It is just a candidate for the active set. And we also have a new candidate for the optimal point. It is not this one, because that is infeasible. This is our new candidate. The point that we would obtain by starting from the previous iteration, going into the improving direction of delta, but we cannot go all the way of delta. We cannot have 1 here, but we will have this beta here. Because the beta essentially says how far we can travel in this direction before hitting one of those constraints. And we must stop at the closest constraint that we will hit by traveling in this direction. So that's why we have to compute those distances. We have to identify the smallest distance. That's our new step length. We have to update the solution by taking the previous solution plus step length times the improving direction. And we also add to the active set the constraint that we have just identified here. And probably the best way how to illustrate this would be by means of an example. So that's what I will do next.